Hey geometers, lesson 4 is going to be your favorite lesson of the entire next 10 minutes. So we're going to talk about using definitions. Now in geometry we've looked at lots of definitions, like what's a segment and what's an angle and all that fun stuff. You can write any definition as a conditional statement in an if-then form. You can also write it as the converse of that conditional statement. So both the conditional statement and its converse are true for definitions. For example, check out perpendicular lines. If two lines intersect to form a right angle, then they are perpendicular lines. In the past, we might have seen like perpendicular lines are two lines that intersect to form right angle. So in if-then form, you say if two lines intersect to form a right triangle, or a right angle, sorry, then they are perpendicular lines. So we can go if-then on that. And now that's our conditional statement. We can also throw it down as the converse. If two lines are perpendicular lines, that's the Q from up here, then they intersect to form a right angle. That's the P from up there. So conditional statement, converse, they're both true. Isn't that cool? And in just case you forgot, here's the notation for the line L is perpendicular to line M. How fun! Let's do an example about using these definitions. Let's decide whether each statement about this here diagram is true. All right, how about, let's start with A. Line AC is perpendicular to line BD. Well, let's see. These are two lines that intersect to form a right angle. Therefore, they're perpendicular. Bada bing, bada boom. The statement is true. The right angle symbol here tells you that these lines form a right angle. So you can say they're perpendicular. Wasn't that awesome? See, I can't play animations. This is so weird. All right, let's look at C. Why? Because I felt like it made more sense to go A, C than B. Maybe not according to the alphabet, but definitely according to the definitions that they're using here. So C says that ray EA, so ray EA starts here and goes there, and ray EB starts at E and goes through B. My picture is so much more neat than theirs. I just wanted you to see what I was talking about. Are these opposite rays? Well, I'm sure that you totally remember the definition of opposite rays. But if not, I'll throw it out there for you. If two rays share a common endpoint, ding, and extend in opposite directions, forming a straight line, then they are opposite rays. Okay, so these two, they share a common endpoint, but they do not extend in opposite directions. They do not form a straight line. So P is false, which means that I cannot conclude that these are opposite rays. So this here statement is false. Point E does not lie on the same line as A and B, right? E would have to be in between them for them to be opposite rays. And remember, in geometry, the definition of the word between means that it's collinear, not just like this point isn't between A and B. It has to be collinear to be between. Anywho, playing animation. B, let's do B now. Angle AE, whoa, timeout. Sorry, I just wanted to erase. Angle AEB, so AEB is this angle right here, and CEB, this angle right here, are a linear pair. Well, shucks. What's the definition of a linear pair? If the non-common side of adjacent angles are opposite rays, so these are adjacent angles because they share the side BE. Ray EB, right? They share that side, so their non-common sides are ray EA and ray EC. If the non-common sides of adjacent angles are opposite rays, see, now you know why I did C first, so we could look at what the definition of opposite rays is. So ray EC and ray AC do share the same endpoint E, and they extend in opposite directions, forming a straight line. So these are opposite rays. Hence, therefore, angle AEB and angle CEB are a linear pair. That is true. That's as true as true gets. Super true. And you want to know what else is true? You're done with lesson 4. That's what. I'll see you later. Stay awesome. Don't be regular. Be amazing.